Day 23, 4.3, Riemann sums and definite integrals. So what we're going to look at today is we're still going to look at area under a curve and talk about upper sums and lower sums, but we're going to focus on what if the subintervals don't have equal widths, meaning if we're looking at rectangles, what if the bases are not all the same? So what we do is, well, first we have to talk about some vocab. The width of the largest subinterval of a partition with this delta is the norm of the partition, and it's denoted by this notation. So this norm is equal to delta x, and it's b minus a over n, and these are when we have those regular partitions, meaning the bases of our rectangles are all equal, okay? But if our largest partition goes to 0, so meaning the width or the base of our rectangle essentially goes to 0, then what that means is n, remember n is the number of rectangles that we have underneath the curve goes to infinity, okay? So the width or the base of our rectangle goes to 0, meaning we have infinitely many rectangles essentially smashed together. So this leads us into some sort of Riemann sum definition, okay? So we're going to let f be the defined on the closed interval and our delta be a partition, okay? Some partition, where this partition is the width of the ith subinterval, okay? So they're not all the same necessarily. And c sub I is any point in the ith subinterval, okay? And this is just that interval. Then the sum is simply just like what we did before, is this delta xi, that's our base, right? That's the width of our rectangle, our base of our rectangle, and this f of ci is the height. It's just saying that for a Riemann sum, the bases aren't always going to be equal, okay? So it's called a Riemann sum for the partition delta. Continuing on, the notation that we're using is if we have this limit as the partition goes to 0, the largest partition goes to 0 of the sum of all of these rectangles, right, from 1 to n. Well, as this partition goes to 0, what that is indicating is that the n, the number of rectangles, is going to infinity. So we can go ahead and say, well, this is the same as saying the limit as n, the number of rectangles, goes to infinity, is equal to the sum of these guys here, okay? Our base, again, is this delta x. Our height is f of that ci. So this is leading us into the definition of a definite integral. So the last couple of videos we dealt with indefinite integrals. So again, we have the limit as our largest partition goes to 0, okay, of the sum of these rectangles. That's what those are representing, okay? Where this f of ci, well, that's our f of x, that's our y value, that's the height of our rectangle. And this delta x, we can consider that dx, which is the base of our rectangle. So this is going to equal the integral from a to b, that's the interval in which we are, of f of x dx. So we can see that those are the same. So that's the limit notation. So let's look at some properties of definite integrals. So one thing to note is a definite integral is either positive, negative, or it's 0. So let's look at these cases. So if we're trying to find the definite integral on the interval from a to a of f of x dx, well, when our interval is just one value from a to a, that gives us a definite integral of 0. Now, if f of x is positive, then the integration on a to b is also going to be positive. So if I'm taking the integral from a to b of f of x dx, this is going to be a positive value, okay? Now let's take note in part 3. If I'm taking the integral from b to a, notice we just flip-flop the order. Well, what I can think about is that's the same as saying the opposite of the integral from a to b. Now I just switched the interval around, and so what that means is this is going to be negative. So it's important to pay close attention to the interval in which you're integrating. Okay? All right, keeping up with some more properties. The fourth theorem, 4.6, the additive interval property, simply says that if f is integrable on 3 closed intervals from a to b and a, b, and c, then we can go ahead and say the integral from a to b is equal to the integral from a to c plus the integral from c to b, if c is going to be in between those guys. The next property that we can talk about is if we have this constant in front, and it's similar to the summations. So again, if f and g are both integrable on a, b, and k is a constant, then the function k times f and f plus or minus g are integrable on that interval as well. So for instance, if I have the integral from a to b of k times f of x, I can pull that k out in front of the integral. And same goes for if I'm adding 2 functions within the integral, I can break it up into 2 separate integration portions. Okay? All right, what I want to do right now is I want you to copy this example down because I didn't put it in our notes, but it's a good practice item. So pause this video right now, and actually I want you to try to write the limit, this limit, as a definite integral on the interval from 0 to 4, okay, where ci simply is any point on the ith subinterval. All right, so write this example down and then give it a shot. Okay, so based on what we talked about earlier in the definition of a definite integral, what we should notice is that this portion right here that I underlined in blue, that represents our f of x. So instead of the c sub I just replace it with an x. So note that here in my integral. The delta xi is just considered dx, okay? And our interval, 0 to 4, that's where I write our integral from 0 to 4, okay? All right, so if you have questions on that, let me know. Okay, so now we're going to get some practice evaluating definite integrals by using the limit definition. All right, so there's a few criteria that we need to meet first. First, f of x is going to be that x squared, okay? And we know that it's integrable on -1 to 1 since it's continuous on that interval. So by definition of integrability implies any partition, that delta, whose norm approaches 0 can be used to determine the limit. Okay, so we have to go back, and when we talked about area, the first video, remember we broke up what delta x was equal to. So delta xi is going to be the same as delta x, which is our interval b minus a over n. And in our case, since our interval is -1 to 1, we have 2 over n for our delta x. Okay. Then to figure out our ci, remember what we said before is ci is equal to the starting value of our interval plus that delta x times I. So we have -1, that's our a. Our delta x was 2 over n, and then we just multiply that by I. So then we need to find f of ci, which is simply f of this guy right here, okay? And that's going to be -1 plus 2 over ni squared. So now we're going to set up using our definition, okay, our limit definition. So we know that the integral, okay, our definite integral is equal to the limit as the largest partition goes to 0, okay, of this sum of our base times the height of all of these rectangles underneath this curve. Okay, that's what this is representing. Well, remember, as the largest partition is going to 0, that means the number of rectangles n is going to infinity. So we can rewrite this limit. And now we're just plugging in. So our delta x is 2 over n, f of ci is this guy here. And now it's just a matter of foiling this, remembering 2 over n, remember n, those are all constants, so we're going to pull those out, okay, and cleaning things up. Now remember, we can break this up into multiple summations, okay, and again, bringing the constants and n out in front of our summations. Now what we need to do is we have to use those formulas, the summation formulas that we talked about in the previous video. Again, you don't need to memorize these formulas, but you should have them handy, at least for the homework and going through everything. So doing our substitutions, remember for the sum of 1, we simplify, or we substitute n for that summation. When we have the sum of I, here's what we substitute. And when we have the sum of I squared, this is what we're substituting here. And you can take a look and clean everything up. And after you get down to it, we end up with the limit equaling 2/3. So therefore, our definite integral from -1 to 1 of x squared dx equals 2/3. Make sure you go through this algebra to prove that you also get 2/3. This next example wants us to use the figure below to find the values. So again, we have to think about integrals as areas under a curve. Okay, so that's what we're thinking of. So if we're looking at part A, the integral from 0 to 2 of f of x dx, well, this whole graph is f of x, okay? And we want to find the area under the curve. Now we're going from 0 to 2. So we're looking at these guys here. So I want this area and this area, and I'm going to add up all those pieces. Well, what we should notice is I can draw a line there, and we essentially have a rectangle, or in this case it's a square, plus a triangle, and notice that this triangle is underneath our x-axis. So this is going to be a negative, okay? So I'm going to take the area of this square, which is 1 times 1. I'm going to add it to the area of this rectangle, which is 1/2. Our base is also 1/2, and the height is 1. And now I have to subtract the area of this piece. So again, we have a triangle, but it's going to be minus our 1/2, our base also 1/2, and the height is 1. So now when we gather everything, the triangles essentially cancel, and we're left with the area of 1. For example B, we want to now look at the interval from 3 to 7. So if I'm looking here, I'm looking at 3 to 7, so I want the area of this piece here. So we should notice that's a semicircle. So the area of that piece from 3 to 7, sorry about the bell, is going to be 1/2 pi r squared. We should notice that our radius, if this is our center at x equals 5, our radius will be 2. So 1/2 pi times 2 squared will end up with 2 pi. All right? For example C, now we're looking at the interval from 2 to 7. So as I look through, I need this piece here, plus again this semicircle. Now notice this triangle portion is underneath our x-axis, so this is going to be negative. So we have -1/2. Our base for this triangle is 1. The height is also 1. And then we have to add the semicircle to it, which we already found to be 2 pi. So we end up with the area, or the integral from 2 to 7, is going to be 2 pi minus 1/2. And finally, for example D, we are trying to find the integral from 5 to 8. Okay, so if we're looking at our intervals, we're at 5 to 8. So we want to find the area of the quarter of a circle and then of a trapezoid, but notice the trapezoid is underneath the curve. So when we go through here, 1/4 pi r squared is going to be our quarter of a circle, and remember a trapezoid 1/2 times our height is 2, times the sum of our bases. So base 1 is 1, base 2 is going to be 1/2. And when we clean everything up, we get pi minus 3/2. These next examples, we're going to sketch a figure to evaluate these definite integrals. Okay, so if we take a look at A, we're looking at the integral from 0 to 3 of 4 dx. Now remember, this piece right here is our f of x. So really f of x equals 4. Well, if we were to graph this function, f of x equals 4, you should recognize that that's just a horizontal line, y equals 4. And we're looking at the interval from 0 to 3. So 0 to 3, and we draw those vertical lines up to our curve. So what we should notice is we have ourselves a rectangle. The height is 4 units, and our base is 3 units. So what's the area, or what's the value of this definite integral? It's going to be our base times our height, which is 12. I want you to go ahead and sketch part B, and now we're just going from negative a to a, where our f of x is still 4. So draw the sketch and then find the area or evaluate the integral. Hopefully you got what I got. So again, it's still a rectangle. Our curve is still f of x equals 4, and we're just going from negative a to positive a. So we still have a rectangle. The length of our base this time, though, is 2a. Height is still 4, so then the area is going to be 8a. Go ahead and try to sketch part C, a minus the absolute value of x. And our interval goes from negative a to a. So what I want you to do is I want you to plug in those endpoints, negative a, and then maybe pick a value in between those to see what we're looking like. Give it a shot and come back. What you should have realized is we actually have a triangle. When x equals negative a, this function, f of x, equals 0. When x equals positive a, again, a minus the absolute value of a is simply 0. But when x equals 0, we're at the point 0a. So we have ourselves a triangle that we're trying to find the area of, essentially, right? We're trying to find the integral under of that. So the triangle, our base is 2a, and the height is a. So area is 1/2 base times height, and we get a squared. We're finally on to the last example. We're going to use the table of values to find lower and upper estimates of this integral from 0 to 6 of f of x. Assume that f is an increasing function. So the first thing I want you to do is I want you to plot those points on the graph that's provided. Go ahead and do that, and then we'll talk about the lower and upper estimates. So I plotted those points using the table, and I connected them. And essentially, we're trying to find the integral from 0 to 6. So when we do that, if you notice what I have highlighted in yellow, that's the area, that's the integral we're trying to find. Okay? So one thing we should notice is this piece here, we've got some negative values. All right, so for the lower estimate, we are going to have, it's essentially our rectangles, right? We're trying to find the sum of these rectangles, base times height. Our base is going to be 1. The height, since we are increasing, the lower estimate is going to be the left-hand values of our rectangles. Okay, so if you take a look at what I've labeled here, that's these pink guys, right? So this is going to be the height. These represent the heights of our rectangles, okay? And what we need to do is we need to use the left-hand endpoint. So our first rectangle, the x value is going to be 0. The second rectangle, we're going to have 1. The third, the left side, is going to be when x is 2, etc., etc. So when we do this, you should see that our lower estimate is going to be 1 times negative 6. And if we're looking at our table of values, the left-hand x values are going to stem from, this is going to be our first, this is going to be our second, our third, our fourth, our fifth, and our sixth value, okay, for the left-hand values there. So our base is always 1. The rectangles all have the same base. So 1 times negative 6, 1 times 0, plus 1 times 8, plus 1 times 18. Our fifth one is 1 times 30, and our sixth is 1 times 50. So when we add these all up, we get the lower estimate to be 100. So what I want you to do is I want you to look at this diagram again, Now to find the upper estimates, I notice those in green. So those are where the heights of my rectangles are, okay? So for the upper estimates, we're going to be using the right-hand sums, okay? So go ahead, give it a shot, and then we'll compare our answers. For the upper estimates, again, we're rectangles, base times height. The base is still 1 because all of the increments for x are the same. The height of these rectangles are going to be f of the right-hand x value. Okay, so the right-hand x value, the first one is going to be 1, is going to be when x is 1, but f of 1 is 0. So we have 1 times 0, plus our second rectangle is going to be 1 times 8. Third, 1 times 18. Fourth, 1 times 30. Fifth, 1 times 50. And sixth, 1 times 80. When we add those all together, we get the upper estimate to be 186. So what can we say? Well, we can say that the actual the actual area under this curve is going to be somewhere between 100 and 186. If you have questions, let me know next time we see each other in class.